So our plan was to see how the amplifier works.
Correct. We have got a big diversion. What shall we do?
So amplifier means we will be operating in some limited region of this
In limited
curve.
region of this. Correct. Correct.
So how shall we represent that? Then input we will have to accordingly apply.
We'll have to accordingly apply carefully, right? Because we can't use it in all regions. It looks very different.
If you give a sine wave of this much wide change in input,
correct,
I'll get a modified sine wave.
You won't get only the sine wave. You'll get all kinds of other things. Right. So we need to use some small thing, small portion.
We will definitely have some harmonics sine.
Correct. Correct. Okay. So then what do we do? We need to maybe take a modification.
We'll modify the input.
We'll do that. So let me make a copy of this.
Yeah.
So we want to start from this,
So we will fix some Vi to
correct,
wherever we want to operate.
Correct.
And then there should be a way to include the signal that we want to amplify.
That is right. Correct. Let's do that. So what I will do, I will so we will fix Vi.
Yeah.
And then you said you also want to add the
signal to be
amplified. We will do it like this.
Yeah.
So this is.
So now instead of Vi, we will call it's a fixed quantity.
It's a fixed quantity. Capital VBE.
Yeah. Yeah.
We'll just call it capital VBE. And this one, I'll call it small VBE.
Small VBE.
Right now. So lot of textbooks use this terminology.
Correct.
If you have a sinusoidal signal that is being applied, they'll use small v and small VB, small b and small e also.
Correct.
They have this elaborate, scheme about what the letter voltage or current should be and what that subscript should be.
Correct.
We will try to follow as much as possible.
Yeah.
Right. So I think the important thing to remember is that this is some Vm sin omega t.
Yeah.
Right. Something that we want to amplify. Okay.
So now what will be V0?
How will we find out V0 now?
So our expression for IC should be still valid.
It's still valid. In fact, this is the one thing that we know.
Correct.
Right. So one thing we have to say is that we should choose VBE, VCC and RC such that the transistor is the forward active region.
Yes.
I think that let us just write that down, no?
Yes.
So right, these are the three things that we have to choose.
Yes.
So BJT. I'm just going to call this FAR. I'm getting
forward active.
I'm getting tired of writing it out fully.
Yeah.
Right? Yeah. This is a precondition. So once you do that, then you can apply this small, and once it is in forward active region, we know this, no?
Yeah.
I think this is valid.
Correct. In fact, we can copy this itself. No?
Correct.
We have the expression for
V0 for all V0, no? So, okay.
That's okay. Also.
No. The full thing didn't get copied, but that's okay. I can fix it.
E power. Now Vi is VBE plus small VBE.
Correct. So did I make a RC?
RC.
No? Correct. Is okay?
Yeah.
Okay. So VCC minus ICRC. IC is nothing but IE not exponential VBE by VT.
Yeah.
So that is VBE is nothing but capital VBE with DC value plus small VBE.
Yes.
Right? Okay.
So the small VBE is the one which is varying.
Is the one that is varying. Correct. Capital VB is constant.
Fixed.
fixed. So clearly we want to amplify this
Correct.
small VB.
Correct.
Let us see this.
So this also means output has maybe two component, one some DC component
Correct.
and the other one is the
Correct. In fact, if you set V small VB to 0, no, we know that there is only going to be DC.
correct.
Right? Maybe we should write that down first.
Yeah.
So when there is no VB,
Yeah.
so we know that IC, let me call that IC naught.
Yeah.
We'll call that IC naught. That is the DC value, and that is going to be I naught exponential VB by
Correct.
VT.
Correct.
Right?
Correct.
This is correct. So
Yeah.
this is the DC value.
Yeah.
Even there is no VB.
Yeah.
And we also know that
Output corresponding to that.
output corresponding to that will be VC. So maybe I am trying to see, we already called that V naught. Should we, so what I will do, I'll make a small change. I'll call it like this.
Yeah.
ICD, easier.
Yeah.
VODC. This will be VCC minus RC times ICDC.
Yeah.
Correct?
Correct.
So DC current is flowing through the transistor and the resistor. VDD minus IR. Okay. Very
So
good.
in the previous curve we got, it may be somewhere.
It may be somewhere here. Correct.
Yeah.
That's correct. So I'll maybe show some.
Oh,
I'll show something like this.
yeah.
So this is IC DC.
Yeah. And V naught DC.
So I think I
Yeah.
will use small this thing everywhere.
Yeah.
Right?
Got it.
Correct. So it will be some fixed point there.
Yeah.
Okay. So when there is no VBE, we know what will happen. Now we need to bring this back, no?
Yeah.
So then, shall we just see, we are having exponential of VBE plus small VBE.
We can separate that.
Separate it out.
Correct.
Okay. RC times IE naught This is okay?
Yes.
I'll also take the picture.
Yeah.
I think it is useful
Correct.
to have the transistor picture also. Okay. So this is the expression for any VBE.
Yeah.
But I see that there are some familiar expressions there. So this is ICDC, no?
Correct.
I think that I noticed it there.
So we can.
This one, no?
Yeah.
This one is ICDC.
Yeah.
Huh?
Yeah.
So, okay. So we'll write this as VCC
Minus.
minus RC into ICDC times
Small VB by VT.
yes, small VB by VT.
Can we expand this exponential term?
I think you are right. We should do that, right? So we know that e power. We'll write some e power x, no?
Yeah.
E power x is 1 plus x plus x squared by 2 factorial plus so on.
So
no?
on.
So
yeah.
on.
Yeah.
So now we can expand this.
Yeah.
So let's expand this first.
Yeah.
So this is 1
Plus VB by
Plus
VT.
VB by VT plus
VB by VT whole square by 2.
correct, VB by VT whole squared times half,
Yeah.
plus
And so on.
right?
Yeah.
So let us maybe now
Hmm.
we will say make some assumption, no?
Hmm.
So let us say that VB is very small.
Yeah. Because X also, it is less than
It is X is less than 1.
1.
Correct. So we'll
So,
say VB by VT.
hmm.
So what we will say, in fact, the assumption. So we'll write it like this. So this is what we are saying, no?
That's true. Yeah.
This is Vm sin omega t is much less than 1.
Yeah.
So basically the amplitude of the sinusoid is much smaller than Vt.
VT.
is Kt by Q, some 26.5 millivolts,
Correct.
no?
For
sorry,
room
26 millivolts.
Correct.
25.9 millivolts.
Correct.
Which means this capital Vm is much smaller than that.
Yeah.
So
Couple of millivolts.
Couple of millivolts, right? Or
So
smaller.
that means this square terms we can, doesn't matter.
Doesn't matter. We can neglect them, no? So then, which means neglect.
Yeah.
Right?
Yeah. Correct.
Then it makes life very easy for us, no?
Yeah.
Now I can see what is happening. So V naught, no?
Yeah.
Is what we started writing. VCC minus RC ICDC.
Yeah. One
1 plus VB by VT.
Yes. Should we keep approximate just for the sake of?
Good idea. Correct. Okay. And now we also know, we found that VODC
Yeah.
is VCC minus RC, right? This also we found out.
Correct.
We'll write it in terms of that. So
So there is a DC quantity, that's the first term.
Correct.
I mean first two terms.
correct. So we said this is VODC
Yeah.
minus RC, right?
Yeah.
Okay, this is okay. I'll write it like this: ICDC by VT
Yeah.
times
VB.
VB. I'll write it like this. So there is a, like you said, there is a DC quantity. There is a portion that depends on VB,
Small VB.
small VB, right?
We want to amplify small VB.
We want to amplify small VB, which means this is the portion we are interested in. As
So this
for the amplifier.
RC ICDC by VT has to be more than 1.
Correct, hopefully, right? That's right.
Yeah.
So this should be larger than 1.
Correct.
Larger than 1 for an amplifier.
Yeah. Yeah.
Because amplify means make bigger.
Correct.
No?
Correct.
So hopefully this thing is larger than 1. Correct.
So one thing, when we made the assumption VB by VT is very small, or VB by VT whole square is negligible. That means if I give a sine wave input, I'll get a sine wave output.
Correct. That is right. Otherwise, you will get sine squared, no?
Correct.
You will get some other things also.
Harmonics will be.
Harmonics will be there. Correct. Correct.
That will be a bad amplifier.
That will be a bad amplifier.
You want to make one particular sound, it makes more sound.
Correct. Exactly. Exactly.
Yeah. So, what is this ICDC by VT? ICDC is almost fixed by us, correct?
It is fixed by us, no? So we decided we are
Capital
going to
VB,
choose capital VBE, VCC and RC.
Correct.
So once you choose capital VBE, ICDC is fixed by us,
Yeah.
right? That is true. So let us note that down.
Vt is also known.
Vt is also known, correct. Right? So via VBE, no?
Yeah,
So we set VBE, IC is set,
correct.
IC/DC is set, and RC is also chosen
We
by
can
us.
select. Correct,
Yes.
correct.
And of course VT is KT by Q, no?
Correct.
Correct. So I think
This IC DC by VT, any specific name for that?
see,
Hmm?
it seems to have, see, V by I is resistance.
Resistance.
So I by V seems to have conductance, no? We
Correct.
saw conductance in one of the
Correct,
classes.
correct, correct.
Except, see, it is multiplying, see, we are giving VBE at the input, at the
Input.
base emitter,
It's a
Where-
voltage, which is a voltage.
which is a voltage.
Hmm.
And this is making some current flow because that is getting multiplied by RC, no?
RC.
We saw this, it is RC times
VB by
VB by VT times IC/DC.
Yeah.
So that is part of some current. So in fact, maybe we'll write it like that. So what we are now saying, this IC, no, is IC/DC plus, now we can now call it some small IC,
Yeah,
right?
correct.
This small IC is now is what you called by VT times VBE. That is this portion,
Yeah,
right? Okay. So what I am seeing is the collector current is some conductance times the base emitter voltage. But base emitter voltage we are giving from the input, no?
yeah,
Collector is close to the output, that's
Output.
on the collector side.
correct.
So it can't just be some normal conductance. See, normal, if you have one conductance like this, current and voltage are directly related.
Yeah,
So we need to give some other name.
this is something more than that.
Correct, correct. We'll give it a different name.
Somehow transferred some information from the base
Correct. To the collector.
collector.
So I like that word. So we'll call it transconductance.
Transconductance.
Correct. And the normal symbol is some small g
G, yeah.
with some m subscript, right?
Oh, that means this gain is GMRC.
GMRC, right? So now the gain of the amplifier is GM times RC, right? So now
To be precise, minus GMRC.
to be technical, minus GMRC.
Yeah.
So VO is VOTC minus GMRC times VBE, right?
Correct.
So this is the gain, like you said, gain of the amplifier.
Yeah.
Oh, nice. We have actually made an amplifier for the first time.
Oh, we didn't realize that.
Yes.
Oh, okay.
That's right. So for the first time, we have used a transistor, given some sinusoidal signal. We have basically got some
amplified signal.
amplified signal. Very interesting, right? And the negative sign means that there is a phase shift. You gave sin omega t, you are getting minus sin omega t
Yes,
at the
yes.
That is normally not
So
such
it's
a big problem.
Inverted.
It's inverted. So this is an inverting amplifier.
Inverting amplifier.
Correct. Correct.
So in the first plot we have, no, there we mark VDC point.
Yes,
Now with the small VBE, it may be varying little bit there.
that is correct. Some small change will be there. So around this one, we are going to change, right?
Something like that.
Something like that. So you apply some VBE. Why did I say IC/DC? It should be VBE, no? I think by mistake I marked this as IC/DC.
Yeah, it's an IC/DC corresponding to
Correct, correct.
VBE,
Corresponding to VBE.
capital VBE.
Correct. No, wrong color. I think I chose this color. VBE
Yeah,
and corresponds to IC/DC.
correct.
Correct, that's what we said. And capital, we will get capital VBE plus some small VBE
Yeah,
around this point.
yeah.
So in other words, it will go back and forth like this, no? At any instant of time.
Yes.
Which means the current V output also will go back and forth like that.
Correct.
Now I understand. Because the slope is very high,
Yeah.
you will get a large change for
The output.
For a small change. So in fact, we have shown it not so exaggerated, but actual amplifiers will have very steep.
Yeah.
Correct. Very steep. Correct.
So this is not VB, no, that you have marked at the bottom.
Correct.
Yeah.
Correct.
Small VB.
Small VB. This will be VO.
Correct.
Correct.
So suppose my input, that small VB becomes large, then I cannot neglect the higher order terms.
You cannot neglect the higher order terms. So what will happen, instead of giving just, if you give Vm sin omega t, you will get sin omega t, sin square omega t, sin cube omega t. And now that sin squared will now give second harmonic, third harmonic, all of that.
Correct.
So you normally don't want to do that.
So this small VB, which is very less compared to VT, any name for that?
We'll just call it small signal.
Small signal, because it's small.
It is very small.
Yeah.
So we'll call it.
So it's a signal for which you can assume there's a linear relationship between input and output.
Correct. The nice thing about this is that there is a direct linear relationship between input and output. Correct. For the signal.
For the signal.
Correct. And since we said small signal, this particular point is called the bias point or the operating point.
Okay.
Right. So this point is the operating point. Of the amplifier, or sometimes quiescent point. There are several names for this.
So bias means that the previous circuit we discussed.
Yes.
We can use that to generate this.
That is correct.
Capital VB.
That is correct. So in fact, in a future class, we will do that.
Okay.
We will do that. We should use that previous circuit that we learned to create this capital VBE and create this IC-DC. So that we create this VODC and VBE and everything, and then around that we have to apply this small VBE. Right? So we have to figure out a way to do that.
Okay.
We will do that. That is most likely our next job.
Okay. Because having one DC, capital VB, and then introducing small signal is not that practical.
That is correct.
It is good for explanation.
That is correct. I think it's going to be very hard to put them in series like this and then connect it to a transistor. No?
I need the signal which is a floating signal, not connected to ground.
Correct.
Small VB.
Small VB. Correct. So we need to figure out a way to do that, to add the two signals. So basically what we want to do, we want to add the two, no?
Correct.
And then apply it to the base emitter.
Correct.
We will need to figure out how to do that.
So it has taken some power from VCC to do this activity.
That is correct.
Correct.
So in fact that power will just be VCC minus RC IC-DC will be the current, right? So in fact VCC, that current is flowing from, that IC-DC is flowing from VCC to ground.
Yeah.
Right? So that is the DC current.
Yeah.
Now that current times that voltage is the power drawn from the battery.
Correct.
Some of that will get burnt in the resistor, some of that will get burnt in the transistor.
Yeah.
We have actually assumed that base current is 0.
Yeah.
So directly on the collector emitter side, it will get dissipated, it will get lost as heat.
So that means if you touch, you will feel a little bit.
You will feel slight temperature increase. Correct.
Depending on the current.
Depending on the current.
Yeah.
That's right.
Oh, actually very nice.
Yes.